right? So I'm recording to the cloud. So if you remember, and even if you don't, you can see right here, we made tables of values to solve for R given a particular value of theta, right? So it's no different with number 9, except I want to have an explicitly defined function, right? So I want to have R solved in terms of theta. And that's only because it's more complicated, or you get a more complicated equation if you solve for theta in terms of R. So you're just better off doing it this way, right? So what I'm going to do is factor the left-hand side. I have a common R. So I'm going to pull out an R. That's going to leave me with a 1 minus sine of theta. All right. And we treat it like a quadratic where we set each factor equal to 0 and solve. All right. So R equals 0. 1 minus sine of theta is equal to 0. The R equals 0 becomes irrelevant, because if you remember last time, I mentioned that if you're solving an ordinary quadratic and you get x equals 0, that's a location, right? So that would be relevant. But in the context of conics, it's a radius. An object that has 0 radius is not an object at all, right? So I'm going to work off of this one, toss that, and we'll say sine of theta is equal to 1. All right. Now, there are other ways to go here. So I could try to kind of steal my own thunder and solve for, try to get it into a rectangular form. So, replace the sine and then solve for y in terms of x. The other thing I could do is just kind of live with this as is. Right. So I'm looking for instances where sine of theta is equal to 1. Now that's unit circle. Now, without getting into inverse sines and things like that, if I know my unit circle, I know sine of theta is equal to 1 when theta is equal to pi over 2 or 90 degrees. All right. And one thing that we learned last time is that if you have an equation, I'm just going to focus on theta. I'm going to use this one. Theta is equal to pi over 2. That means theta is always equal to pi over 2, regardless of R. All right. So theta is pi over 2 for all R. All right. So that means my R value could be a 1 in the direction of pi over 2, would put it here. It could be a 2, it could be a 3, a 4, a 5, it could be 4.4, it could be 1.8, it could be negative values going the opposite direction. Same deal. What this is doing is it's creating a path that is in the form of a line. All right. So doing a little bit of the algebra made it a lot easier to handle the graph. Now, I actually haven't done this problem using the grapher, so I'm kind of curious. So let me go to grapher, wipe out this one, add an element, and you can see you can put in a variety of different forms as long as it's an equation with 2 variables. So I'm going to put in R minus R sine theta. And again, I haven't tried this yet, so it'll be nice if it works, but I'm not going to be shocked if it doesn't. Not going to be shocked. Yeah. All right. So I'm just typing in the original equation as it was given. Now I'm just curious to see. No, not handled. Okay. Oh, it was worth a thought, or worth a try, I should say. Now let me see if the other form works. If I just do theta equals pi over 2. Oh, look at that. I mean, that's wrong. but it does correctly say that it's a vertical line. Yeah, nah. I guess it just doesn't handle these as well as I would like them to. One last thing I just want to check. No, that one's too complicated. R is equal to, nope. Come on. Dang it. Alpha R shift pi equals 1/2. Pretty sure I did this one at some point. Yeah. So it handles some of them. It just doesn't handle all of them. So, it'd be nice if you could just type everything into a calculator and it works out perfectly, but it's not always the case. And, it's possible that in a future update, it'll be something that's supported, or maybe it already is supported and I just don't know how to do it. Always a possibility. All right. So on page 13, we're going back to the problems where we convert from one form to another. So if we have X's and Y's, we want R's and thetas. All right. Now, I don't want to have to scroll back and forth, so I'm just going to write it here. X is equal to R cosine theta. Y is equal to R sine theta. Now, before you do that, you may want to try to clean it up a little bit. It's not always the case that you can, but if you can, you should. All right. So in this case, the only thing I could really do is multiply everything by 4. So multiply the entire equation by 4, you get x squared minus 4y squared is equal to 4. It's a very minor step, but it makes it so you're not dealing with a fraction anymore. In the absence of something else meaningful that you could do, that's always a good thought. If there's fractions, just try to get rid of the fractions. I'm replacing x with R cosine theta and y, just the y, with R sine theta. That x squared becomes R squared cosine squared theta minus 4 R squared sine squared theta is equal to 4. All right. Now, ultimately, the goal here, and based on these instructions, is just to get it in terms of R's and thetas. We were done with that in this step here. All right. But just for curiosity's sake, I'd like to take it a little bit further and try to solve for R. I noticed that there is a common R squared here and here, so I'm going to factor that out. So I have R squared cosine squared theta minus 4 sine squared theta is equal to 4. If ultimately my goal is to get R alone, then I'm pretty much there. I just got to take cosine squared minus 4 sine squared and divide it into both sides. So it's going to be not very pretty here. I'm just going to move this over a little bit. So dividing both sides by cosine squared theta minus 4 sine squared theta to both sides. All right, so it cancels on the left, and you're left with just an R squared equals all of this stuff. And then, just the last little bit there would be to take the square root of both sides. All right, so it would be R equals this under a radical. All right, now the R value being positive or negative, when you take the square root, technically it's a plus or minus. So you could put that in there, it doesn't always end up making a difference when it comes to polars, because the R value is just the direction you're taking toward or away from a particular angle. But, be on the safe side, if you're not graphing it, you might as well just have the plus or minus there just to be safe. All right. So that had some oomph to it. I mean, a lot more writing, but it still, didn't do really much beyond basic algebra, which is good. Right. And you can see, if you compare this to number 16, you see that they're essentially the same thing, or at least they have the same ingredients. You have a constant on the top of a fraction that's under a radical, a coefficient of cosine squared, in the case of number, whatever this one was, 12, that coefficient was 1, but still coefficient, and a minus sign. So basically what it's getting at is these two function or equations are really the same thing, same type. All right. So if I tell you that this is a hyperbola, and it leads to this form in polar coordinates, then anything that looks like that is also going to be a hyperbola. And if you're like, okay, what's a hyperbola? We graphed one of those last time, right? So it's basically the appearance of two opposing parabolas, right, that make up the same function, or in this case, equation, because, in the XY plane, it's not a function, but in polar coordinates, it is. So it's, it's just the way things kind of shake out in terms of the semantics. All right. But yeah, before we get to number 16, let's do number 14. All right. So a couple of reminders. R is equal to the square root of x squared plus y squared. Sine of theta is equal to y over r. All right, those are all indicated above. I'm actually just going to shrink this down a little bit because I don't want it to appear that these are continuation steps. All right. Now, kind of an addendum. This is the same as saying r squared is equal to x squared plus y squared. All right. And so you'll notice, if we were to go the other way, these two are kind of interchangeable. One leads to the other. If we wanted to go from this to this, we just take the square root, but you'll see how in this case, the negative is not there. It's not a plus or minus. Okay. So it's just kind of further evidence that these plus or minuses don't have the same meaning in polar coordinates as they do in rectangular coordinates. Right. Before I get into swapping out the r, we talked about this last time, it's the best bet is to try to swap out the sine function, because sometimes you can kind of combine like terms and get those r's to consolidate and collapse into just one term. All right, so r plus 5y over r is equal to 0. I'll rewrite that as r plus 5y over r is equal to 0. All right, I want to get rid of fractions like I did in the previous problem. So I'm going to multiply everything by r. That gives me r squared plus 5y is equal to 0. And r squared is x squared plus y squared. All right, that's this relationship here. So now I didn't even have to bother with the radical. Plus 5y is equal to 0. Now, later on, we're going to talk about how we can get this into a standard form, this one here. All right. And it has to do with the y squared plus 5y, right? When you're dealing with that, we could complete the square to clean it up, but it's a different problem for a different moment in time. So we're just going to sit tight on that, right? So for now, we're just leaving it like that. We also kind of got the idea that in some instances, you're better off being in polar form. So that's this case here. This is much easier to graph. I mean, even if you're just considering it as like what you have to type into the calculator to get a graph, this is going to be much easier than this. Right. So part of what we're doing here is strategically determining which form is better than the other and making a decision. Well, we're determining which form is better than the other, and we're using a strategic approach to create the graph. Right. So I'm just going to show you real quick. If I had solved this one for R, it would be -5 sine. Oh, I had it on the theta to begin with. All right. So that's a circle. Its radius is 2.5. And it's centered, well, it looks like around -2, 0, -2.5. All right, somewhere in that neighborhood. All right, so we could plot this fairly easily. All right, but recognizing that this is a circle gets me to think, okay, well, can I come up with the equation of that circle without having to do all this work? All right, so I'm going to steal my own thunder a little bit, even though I just said that I wouldn't. Well, technically I said I would save it. It's a problem for a different moment in time. Well, technically this is a different moment in time, but I just did a complete 180. All right, so I changed my mind. All right, so a circle equation is x minus h squared plus y minus k squared is equal to r squared. All right, h and k represent the center. R is the radius. So if you can pull the center and the radius from an image on your calculator, then you can do the conversion without having to do any algebra. So I'm just going to pop that in here, mark it up. Well, let me shrink it and then zoom in. All right. So, and you know, based off the scale, it's kind of hard to tell where the center would be. You can always change the scale. You just go with your axes, you know, just kind of bring it into the right neighborhood. My x min and x max, that seems fine. So I'll just leave that alone. My y min looks like I want to be around -6 and go to 0. And it rescaled it a little bit because, you know, when you do it manually, it takes off the setting that that the scale, the vertical scale, horizontal scale can be whatever the computer decides. It defaults to integer values where applicable. So in this image, it looks like directly between 2 and 3 is where the center would be. So right here. So that center is 0, -2.5. The radius is the distance from the center to any point on the circle. And while you may want to find this distance, which would be fine, it's easier to find this distance, which is 2.5. So when I write the equation of the circle here, all I'd have to do is replace the h value with the x value of the center, the k value with the y value of the center, and the radius with, you get the idea, whatever the radius is. All right. So I can now write this as x minus 0 squared, or just write x squared, plus y minus negative 2.5 squared is equal to 2.5 squared. Now that's like a little much in terms of writing it that way. It's a lot nicer to write it as x squared plus y plus 2.5 squared. The 2.5 squared at the end, you could write that as the decimal. I think it's 6.25, or you could you just leave it as 2.5 squared. I mean, that's not the point of this. I'll write 6.25. All right, so this is what this would become if we completed the square. All right, but the good thing is we don't have to complete the square if we know a little bit about the graph, right? And also, it kind of seems like if you're given an equation, now I kind of jazzed it up a little bit. The true equation here would be r is equal to -5 sine theta. All right. There's some attributes of polar graphs that, well, let me just show you. We talked about this a little already, but it didn't matter at that point. Now it's starting to matter. All right, let me do 5 sine theta. Plot the graph. Nothing's on the screen. That's because I changed the settings. It's the same circle, but now it's above the x-axis. All right. Now, if I change it, but still centered around the y-axis, if I change it to cosine, and plot that graph, now it's in the positive side of the y-axis, or it's on the positive side of the y-axis, and it is centered on the x-axis, right? So I stole all my room here, so I'm going to just jot this on another piece of paper real quick. If I have an equation and it's in the form of r equals a cosine theta, if a is positive, even before I get to that, the cosine theta means that its axis of symmetry is the x-axis. All right, if a is positive, it's to the right of the y-axis. If a is negative, you guessed it, it's to the left of the y-axis. You could also have an equation that's in the form, oh, and by the way, these are circles. All right. So same idea here. If I have a sine theta, also going to be a circle. The axis of symmetry is the y-axis. And then whether a is positive or negative determines if you're above or below the x-axis. Above the x-axis. A is negative, below the x-axis. right? Now, oftentimes people don't bother with this information because it's like, well, this only works for circles. So what happens when you're dealing with a hyperbola or an ellipse? How does it play out? Well, the short answer is differently. So you'd be forgiven if you were like, I'm not going to really bother memorizing these relationships because, not every problem is going to be a circle. And that's fine. It's just information. All right. If anything, you have that information and you could just kind of go off of that, kind of look at it as like a sort of a fun fact of the day kind of deal. Or you never know, it may come up in another class. I highly doubt it, but it's cool to make these kind of observations. Like, oh, this always works. You create a rule that way, right? So more than anything else, it's to avoid having to do complicated algebra if you recognize where the circle lives. And actually, before I get on to another example, let me just, I'm gonna do that. Before I get on to number 16, let me do another example. Let's say I have an equation, y equals, I'll try to keep the numbers a little nicer here. I'll say -6 cosine theta. All right. So what I know about this is that it is a circle. It's got y-axis, x-axis symmetry. And it's to the left of the y-axis. And also, the radius is equal to 3. All right. It's one thing I kind of glossed over. That a value is twice the radius. How do I know? Well, when we did 5, when we had a coefficient of 5, the radius was 2.5. So it's actually this number here, whatever the coefficient is, that's your diameter. All right. So you could look at it this way, but I like to draw a quick sketch. So it's going to be symmetric about the x-axis. So it's going to look something like this. One of the points, when it's in this form, one of the points is the origin on the circumference, or the pole, depending on what axis you're looking at. I'm sorry, what coordinate system you're looking at. So right here is where my center is going to be. If I know the diameter is 6, then the radius has to be 3. So that's where this 3 comes from. That makes the coordinates of the center 3, 0. And if I go back to my standard form for a circle, I can replace the h with the x value of my center, the k with the y value of my center, and the r with the radius. So x minus 3 squared plus y minus 0, so y squared, is equal to 3 squared, which is 9. All right. Now, I would even further this by saying, maybe I don't care about the actual equation in rectangular form. I just want the attributes so I can draw the picture. All right. So if I'm looking at something like y equals -6 cosine theta, and I know it's a circle, radius of 3, x-axis symmetry, and it's left of the y-axis, then I can just plot the circle and be done with it. If that's the ultimate question that's being posed, then why go further? All right. So just something to think about. Think, like something to think about. Think is the first word of the day. Think. Like, I think I probably should have typed these notes up and included them in the packet. That's what I think. I'm sure some of us also think that. Like, oh, as much fun as I had writing all this down, I think it would have been nicer if it was typed. I think you might be right. All right, so number 16. I'm just going to continue. I'm going to insert another page. I'll clean up the notes later on. I just didn't want to have to smush it in there just to resize it all later. So for number 16, again, our goal is to get it into a rectangular form. One thing you may want to consider is actually just going back. The last thing that we did was we took the square root. So let's undo that by raising both sides to the second power. So r squared is equal to 6 over 2 cosine squared theta minus 3 sine squared theta. Yikes. All right. And I'm just going to put the useful rules on the side here. R squared is equal to x squared plus y squared. Cosine of theta is equal to x over r. Sine of theta is equal to y over r. So I can make the substitution here, but I don't want to regret it later on because maybe I'll get lucky and the r squared will cancel out. I don't know. So let me work the cosines and sines first. And by the way, I'm not going to say that this is the reason why we learned about trig identities, but it's a contributing factor. The idea is that we could manipulate trigonometric equations and expressions as if they were algebraic equations and expressions. Right? So to be able to go back and forth seamlessly, it does help going down the line in Calc 1 and Calc 2. All right, so x over r to replace the cosine, y over r to replace the sine. All right, so r squared is equal to 6 over, well, this is going to be x squared over r squared, and I'm going to multiply that by 2. So I'm going to write it as 2x squared over r squared. This one would be y squared over r squared. I'm going to multiply that by a -3. So I'll put the minus in between. 3y squared over r squared. I have a common denominator within my denominator. So 2x squared minus 3y squared all over r squared. Little keep change flip action. This 6 I could think of, I'm just going to kind of elevate it. Make that a 6 over 1. Little keep change flip makes this 6r squared over 2x squared minus 3y squared. I have a common r squared on both sides of the equation. So I can divide both sides of the equation by r squared. All right, so I get 1 on the left side and 6. So basically cancel to 1. All right, gets a little messy when I do it that way, so I'm not going to, but that's essentially what's happening there. 2x squared minus 3y squared. And then we can cross multiply. That 1 is really a 1 over 1. So I have 2x squared minus 3y squared is equal to 6. It was actually at this step where you could have stopped because it's in terms of x's and y's. So mission accomplished, but this is definitely a little nicer to look at. All right. So just algebra. If you really think about it, I made 2 polar coordinate steps. And they're really just variations of the same step. Replace the X, replace the Y, and then just algebra the living daylights out of it. All right, so don't skimp on your algebra. It's really what the moral of the story is here. On the next page, we have the classical curves. Now, they're designed to be problems that you could just, if you know the form, you could identify the type of classical curve or conic section. It could be a conic section, but that's what we were just talking about. All right, so these classical curves are things that you probably never graphed before. Okay, the first one is a rose, although it doesn't look like a rose. It looks more like propellers, but the idea is that you have petals, like petals in a rose, but still it doesn't look like a rose, so I don't know why they call it that. A lemniscate. I mean, I wouldn't I think we'll all agree that that also looks like a propeller rather than some special term called a lemniscate. Right, so the limousin is a it's a lima bean is really what it is. It's a lima bean. All right, so yeah, that's the lima part of it, I suppose. Although, I mean, I guess if you blur your vision a little bit, you can see why they call it a lima bean or a limousin. A cardioid. That one, I mean, if you don't look at it sideways, I mean, if you do look at it sideways, so turn the page so that this is on the top end. I can actually do that for you. I hit copy. That's not going to work. Oh, it worked. Look at that. All right. It kind of looks like a heart, kind of. The problem is, I could do the same thing with the limousin and end up with something that looks like a heart, if I flip it. All right. So you look at the structure of the equations between the limousin and the cardioid, and you see that there isn't a whole heck of a lot of difference. All right. If the coefficients are the same, it's a cardioid. If they're different, it's a limousin. All right. And then, of course, you have the spiral of Archimedes. Regardless of whose spiral it is, Archimedes or otherwise, it's a spiral. So that's probably the easiest one to identify. It's also the one that doesn't have any trig in it. All right. So if you look at every other classical curve, you see that there's a sine or a cosine in there. And when I say there's no trig in there, I mean, it's not factual. I mean, it's got a theta, so it has trig in it. But what I mean are trig functions. All right. So R is equal to a theta. So some coefficient of theta. So let me just show you real quick. I put 5 theta. Says it recognizes that as a polar equation. I plot it, and it gives you the beginnings of a spiral. If I zoom out, it'll give me more. Right? I have mine in degree form rather than radian form. It still works the same way. We tend to stick with the radian stuff, because otherwise, it's not a matter of like it won't work if you go degree form. It's more like the scale is going to get out of hand very, very quickly, right? Because if you think about it, in order to go one full turn around a circle, you have to travel 360 degrees. 360 1 degree units. So your x-axis has to be labeled out to 360 whatever, because at least that, because you're multiplying 360 potentially by a coefficient. So if I multiply that by, I'll say something small like 10, you're already out to 3,600 units in the x-axis. Right? It gets out of hand very quickly. But if we put theta in radian form, 360 becomes 2 pi, which is about 6 and change, 6.28. My scale is not going to become obnoxiously large if I go 10 turns around a circle, right? Or around the spiral. It's only going to go, it'll be in the 60s, 62.8, right? Much more manageable than 3,600. All right. So that's why we tend to go in radian form. And there's also other calculus reasons, because the radian measure is treated as a linear measure. And so it can be compared with other linear measures. Whereas degrees and, let's say, degrees and inches, that's apples and oranges, two different scales. You can't plot inches on a scale that involves degrees, right? That doesn't equate. All right. So I'm looking at number 17. I have 3 plus 3 cosine theta. Match it up. Looks like this. All right. What I want to do is graph something that looks like that, just on the polar coordinates. All right. So this isn't like all this stuff here is not like a shortcut. It's more like an idea of what you should end up with in terms of the appearance of your graph. Right. It should look something like this. That's the idea. All right. So we could do it the same way we did the graphs last week. Make a table of nice values for cosine. So I have theta. That's going to give me an R. The nice values for cosine: 0, pi over 3, pi over 2, 2 pi over 3, pi. And if we don't have an idea of what's going on by then we can continue going, but we should have an idea, because if it's going to look like this and we get only the top half of it, then by symmetry, we should also have the bottom half of it, right? So we keep that in mind, that these graphs are symmetrical, right? So in the case of the rows, it's symmetrical through any petal. All right. This is the easiest one to show, so I do that. Same idea here. Through any petal, you have symmetry. I don't know why I bowed like that. That's weird. All right. I think the lemniscate is obvious. I mean, you could actually go through the petal, or you could go this way. Either way, you'll have symmetry. Same idea here. And here, the only one that does not have symmetry is the spiral of Archimedes. Right. So once you identify your symmetry, then you're good. Also, that darkened point in each one of the graphs, that's the pole. All right. So now I kind of lost the darkening, but this is a pole, or the pole. So here, 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 here. So, I might as well plot it here and here. So your line of symmetry, if it exists, is going to go through the pole. So that helps also. All right. So I plug in a 0. Cosine of 0 is equal to 1. So 3 plus 3 times 1 is equal to 6. All right. I have 1, 2, 3, 4, 5 rings. I can ballpark the 6 in terms of the radius. So what this is saying is go 6 steps in the direction of 0. 0 is here. I'm going to go 6 steps towards that. 1, 2, 3, 4, 5, and I'm going to call this 6 here. I'll do it in red. That looks like it's about 6 units. Pi over 3. So 3 plus 3 times a half. So 3 plus 1.5 is 4.5. So 4.5 comma pi over 3. All right, so in the direction of pi over 3, we're taking 4.5 steps. So a lot of estimation here. That puts me about right there. Pi over 2. So 3 plus 3 times cosine of pi over 2 is 0. So that gives me 3 steps in the direction of pi over 2. Two pi over 3. So 3 plus 3 times a negative 1/2 is going to be 1/2. Oh, sorry, 1.5, because it's 3 minus 1.5. So 1.5. So 1.5 steps in the direction of 2 pi over 3. So about right here. And then for pi, 3 plus 3 times negative 1 gives me 0. So that's 0 steps in the direction of pi. But 0 steps, regardless of the direction, is always going to put you at the pole. All right, so now I have this part of the graph. Sorry, my little shaky writing there. Oh, that's not much better. Like that, kind of. All right, now by recognizing this as a cardioid, I know that it's supposed to look like this. I have the top half, I now need the bottom half. But since it's symmetrical, I can assume all those points. All right, so just plotted 1, 2, 3. Pi over 3 would correspond, if I flipped it over the x-axis, that would correspond to 5 pi over 3. So 4.5 steps in the direction of 5 pi over 3. And now I have enough to graph the other part of my cardioid. And that's my graph. All right. So taking advantage of symmetry really goes a long way. Now, we kind of overdid it with some of the plots that we made last time, but that was only because we're still learning the attributes of the graphs. So like in essence, we didn't know that there was symmetry until we, kind of went nuts with the table of values and said, oh, look, there's symmetry. Now I can take advantage of that for every other time that I make a graph. So it's about making observations. All right. Pop a star on number 18. Similar type of problem. Grab that next time. Number 19. Sine of 2 theta. All right. I mean, there's a 6 there. I'm not going to neglect that, but it's 2 theta. So what I would do is I'd look in my structures here, and I see that the only equation that has something other than just a theta is that of a rose, right? A cosine n theta, a sine n theta. All right. Now you'll see here, I mean, if you look at the diagrams, we have a rose with 8 petals and a rose with 3 petals. You could have a rose with 16 petals. Like how many petals are there? We don't necessarily know that going in, but we'll figure it out. So I know what I'm structurally looking out for. I'm looking for something that looks like their version of a rose. I need nice values for sine. The problem is, since it's 2 theta, I actually need nice values for sine of 2 theta. All right. So I'm just going to kind of play around with it real quick in my calculation menu and say, all right, well, normally pi over 6 would be a nice value for sine. If I take that and multiply it by 2, I get pi over 3, which is not a nice value for sine. All right. But if I have pi over 12, multiply that by 2, I get pi over 6, which is a nice value for sine. All right. So what this is telling me to do here is take the nice values for sine and divide by 2. All right. Why 2? Because that's the coefficient. All right. Zero is nice no matter what you multiply it by. So not worried about that. Pi over 12. So pi over 6 would be my first nice value ordinarily, divided by 2 gives me pi over 12. My next nice value for sine would be pi over 2. So I'm going to divide that by 2. So pi over 4. My next nice one would be 5 pi over 6. Divide that by 2. We get 5 pi over 12. All right. And then the next one after that would be pi divided by 2 is pi over 2. All right. So we may need more table before it's all over, but we at least have something to start with. And also we kind of, we thank whoever came up with the polar graph that's measured in increments of twelfths. And it seems to work out nicely for us. All right. Now, I mean, if it said 6 sine of 17 pi, I'm sorry, 17 theta, I mean, there's no universe where you divide by 17 and end up with a series of nice numbers. All right. So I have 6 as my coefficient across the board. Sine of 2 times 0, so sine of 0 is 0. So my coordinates, again, r comma theta would be, in this case, 0, 0. 0 steps in the direction of 0 is just 0. I'm sorry, it's just the pole. All right, pi over 12 doubled is pi over 6. Sine of pi over 6 is 1/2. So that gives me a 3. So 3 steps in the direction of pi over 12. Pi over 4 doubled is pi over 2. Sine of pi over 2 is equal to 1. So 6 steps in the direction of pi over 4. I'm going to put me about right here. Pi over 12, or 5 pi over 12, doubled is 5 pi over 6, sine of which is negative 1/2. So -3, 5 pi over 12. So 3 steps away from 5 pi over 12. So that's going to be down in this neighborhood. 1, 2, 3. Two times pi over 2 is pi. Sine of pi is 0. 6 times 0 is equal to 0. So that's another 0 radius. This is just pi over 2. So no help there. All right, because we already have a point at the pole. So we have some disconnected points in the middle of nowhere, but it's starting to form a pattern. All right. If I assume that it's going to look like this. Now, by the way, we really don't have to make assumptions because we have a calculator. We just type it in and take a look. But that being said, if I'm assuming that it's taking on this pattern, then this must be a line of symmetry. So I can assume another point over here in order for it to have that symmetry. All right, so one pedal down, but I know there's got to be more because there's another point over here. All right. Now, if we go back and look at our guide, we can see that we could have an odd number of pedals or an even number of pedals. So we have two choices here. One would be to go to the calculator. The other would be to continue with nice points for sine. All right. So I'm going to do a few more and see if it gets me where I need to go. And if not, I'll kick over to the calculator. All right, I'll resize all this in a couple minutes. But the next one, so I left off at half of pi. The next nice number for sine would be 7 pi over 6. So we'll do 7 pi over 12. Then after that, it would be 3 pi over 2. So chop that in half, 3 pi over 4. Then it would be 11 pi over 6. So 11 pi over 12. And then it would be 2 pi, which would get me to pi if I divide by 2. All right. So 6 times for each one of them. And again, this is all work for the same problem. Problem, as in this is a really long problem. Or, man, I'm going to have a problem if I don't start getting to know my unit circle numbers. Problem is the second word of the day. All right, so if I put 7 pi over 12 in for theta, it becomes 7 pi over 6, the sine of which is -1/2. So I have -3, comma 7 pi over 12. So that's telling me that I'm looking at 7 pi over 12 and taking 3 steps in the opposite direction. So here's 7 pi over 12, standing at the pole, going to go 1, 2, 3 steps away. If you get confused, just look for the ratio that has the same denominator, right? That's the one that'll be on the same line. So if I want to go opposite 7 pi over 12, I go into the fourth quadrant and I find the one that has a denominator of 12 that's close to being on that line. 3 pi over 2, sine is -1. So I'm looking at -3 pi over 4, and I'm going to take 6 steps in the opposite direction. So that's going to put me down around over here. And it's at this moment that I just caught a mistake. Right, back up here, because I'm wondering why this looks like this. 5 pi over 12 doubled is 5 pi over 6. Sine of 5 pi over 6 is equal to +1/2 times 6 is equal to a +3. So this should have been 3 steps in the direction of 5 pi over 12. So this point shouldn't be there, which actually kind of stinks because we already have 3 steps in the direction of 5 pi over 12. Although I'm struggling to figure out why that's the case. I think, just double checking. Oh yeah, weird. Sometimes I have no explanation. So I plotted, even though I had a -3 here. Sorry, wrong tool. Even though I had a -3 here, I still plotted it as a +3. And so it was my brain trying to do a course correction, and it ended up not jiving with what I wrote down on paper. Good. Okay, so we're back on track now. It's weird. You know what I did? I know exactly what happened. I plotted the 3 because of the symmetry. But then that's what should have been there to begin with. That -3 was the one that was the aberration. Strange. 11 pi over 12 times 2 is 11 pi over 6. Sine of 11 pi over 6 is equal to -1/2. So I get -3, 11 pi over 12. So at 11 pi over 12, which is over here, I'm going to take 3 steps in the opposite direction. 1, 2, 3. And that jives with the concept of symmetry, where I have another petal, and right down the middle, it has symmetry. All right. Now, this is where it all kind of takes off. And by the way, I have an extra computation here that I'm not going to do anything with, because at pi, sine is 0. And Lord knows we have enough instances where there's a 0 involved and it doesn't contribute anything. All right. We have to have symmetry through any of the petals. So I must have symmetry over this line, which means that there has to be a petal over here somewhere in order for this to work out. So what I can do is I can reflect any of these petals to the opposite side of that line. All right. I'm going to get a point here. Along the over 12s, I'm going to have 3 and 3. All right. But I also have to have symmetry really over any of the lines. Right. So this rose petal needs to be reflected also. So that's going to go over here. So it took a while, but after all of this, we're able to come up with a fully symmetrical, oops, that's hideous. A fully symmetrical 4-petaled rose. All right. So the natural question, well, I guess there's a lot of natural questions that could come out of this. One would be, I think probably the most pressing one to address is there an easier way to do that? You know, it's a legitimate question. There are easy things that you can keep in mind. In a rose, if the coefficient is even, then the number of petals will be equal to twice that value. All right. So I know that's kind of a wordy way of saying it, but given R equal to A sine, it doesn't matter if it's sine or cosine of n theta, if n is even, then number of petals is equal to 2 times whatever that n value is. As it turns out, if n is odd, then the number of petals is equal to just n itself. All right. So if this says sine of 3 theta, there will be 3 petals. If it says sine of 19 theta, there will be 19 petals. But if it says sine of 6 theta, there's going to be 12 petals. All right. So whatever the coefficient is, if it's even, you double it. If it's not, you keep it the way it is. All right. Now, in terms of the calculator, six sine theta plot the graph. Sorry, 6 sine 2 theta. I'm going to arrange the pores. All right, so we get that graph, which, definitely looks a little nicer than mine. The problem is you got to be able to pick out some points to plot on the polar coordinate system. All right, so you can go by, if you want to do some kind of calculation where you pop in a theta value, let's say pi over 12, it'll plot the information for you, but it doesn't give it in nice numbers. That pi over 12 that I just put in there, it came back as 0.262. And then an R value of 0.05. Oh, actually, sorry, that one's on me. Well, it's all on me. It's radians. All right. It'll tell you that it's 3. It's telling us that it's 3.000000076, but it's trying to say 3, right? So you can get that, you can get it that way. You can navigate your way around and try to get nice points. The problem is the theta value is never going to be nice, right? A theta, if it's in terms of pi, it's extraordinarily nice, but it's not. It's multiplied by pi and given in decimal form. So that kind of stinks, right? But you can get the R values. And then what you can do is take an approximation of that decimal, go back to your home screen, and then, you know where that point is in the graph. You know it's somewhere in this neighborhood. They're like, okay, maybe it's pi over 3. No, maybe it's pi over 4. Oh, look at that. Same decimal. So there you can pull out the actual value in terms of pi to get your points. You could also just kind of wing it, or at least try to. That looks like it's at a 45-degree angle. Maybe you don't agree, but if I were to draw a line, just like I did over here, I keep going with the wrong tool. If I draw a line on that graph, it looks like it's coming directly out of the origin, following the path of y equals x, which is 45 degrees. So you do it that way too. All right. You could also try to learn some of the relationships that exist. All right. So for the sine function, which we have here, regardless, let me just show you real quick. Let me make that a 3. The sine function for odd coefficients is going to be symmetric with the y-axis. All right. The cosine function will be symmetric with the x-axis. So you could rely on that. But then with the even coefficients, it can go pretty much any which way. All right, this one has symmetry where the petals go through the x and y axis, but the one that we just didn't. But at least for the odd ones, you can kind of get an idea. All right. So, and also the radius is the coefficient. Whatever the coefficient is the furthest distance any of the petals will have away from the pole. Right. So if you want to go the other way, put in the function first. So -7 cosine. Sorry, that's supposed to be 3. I had negative on the brain. -7 cosine 3 theta. Plot the graph, and then kind of work it out from there. You could, at least you'll have some points to get started with. All right. So I know that it's going to have 3 petals. it's going to go out as far as 7 units away from the pole. All right. So when I'm plotting this one, without doing anything else, I know that I'm going to have a point. We'll call this 6. We'll call this 7 here. We're going to have a point that's as far out as this location. We know the pole is involved, but then we have those other angles not so sure about. All right. So what you could do is you could look at it and say, well, I know that I'm going to have a value that's in the neighborhood of these numbers. So let me just work on those numbers for now. A little thinner. So if I say, all right, I suspect it's in the neighborhood of, I'll say 5 pi over 12. No, I'm going to go pi over 3. So -7 times cosine of pi, right? Because pi over 3 times 3 is going to be equal to pi, right? So cosine of pi is -1. 7, or our theta value, is going to be 7 steps in the direction of pi over 3. So I lucked out. I mean, it was more of an educated guess, but still, to get it on the first try is kind of nice. All right, so we're calling this 7 units away. And also, it looks like the pedal that's going downward in the 4th quadrant seems to have the same angle. So I'm going to assume that 5 pi over 3, 7 units, again, 1, 2, 3, 4, 5, 6, 7 units away, is going to put me in that neighborhood, right? I can verify it by putting in a 5 pi over 3, -7 times, if I multiply 5 pi over 3 by 3, I get 5 pi. All right. So if we deal with coterminal angles, that's equivalent to pi. All right. Cosine of pi is -1. We get the 7 that way. I just need the other points. All right. So I suspect, because if I'm going to just go to navigate real quick. This point here, 1.047, that's the pi over 3, and that's 7 units away. This point, whatever point I'm going to have like over in this neighborhood, has to be closer to pi over 2. And the only one that I have that's closer to pi over 2 without being on the axis itself is 5 pi over 12. So I'm going to grab that one. So -7 times, well, if I multiply that by 3, it's really 5 pi over 4, which is negative radical 2 over 2. Not ideal. All right, so that's going to give us, well, 7 radical 2 over 2. I mean, that's not very pretty, but it's my only option, all right, in that neighborhood. So I'm going to use it. It'll give me a decimal. Oh, by the way, this is 7, 5 pi over 3. So 7 radical 2 divided by 2, like just shy of 5. And it's close enough to 5 that I'm just going to call it approximately 5. So we're looking at about 5 pi over 12. So 1, 2, 3, 4, about 5. You know, you make the point big enough, it'll look like a 5. Right. So that's one little sliver of pi, like slice of pi, to the left of pi over 3, which is the axis of symmetry. So we can assume that we're going to have another point at pi over 4. Right. And you can verify it. You know, it should give us the same about 5. Right. And if you want, -7 cosine 3 times pi over 4, you get the same approximate value. And it helps to know how many points I'm supposed to have. Sorry, how many petals I'm supposed to have, which is where that relationship comes into play, where we say, well, we have an odd coefficient, so we're going to have, well, what's the coefficient? 3, so it's going to have 3 petals, right? But I also know that all of these other petals have to have the same characteristics. So I know I'm going to have a point here and here. One of these days. And I know I'm going to have a point here and here. And that's my 3-petaled rose accomplished with really only 3 computations and knowledge of the nature of the function. Honestly, I don't know why number 21 is there. That's a circle. I mean, I'll draw it, but it's not, it's not a classical curve. I mean, not defined as a classical curve in this context. You know what? I'm not even going to bother with it because we already did like 5 problems like this. So, all right. So that's the nature of the polar coordinate system, right? The basics of it anyway. All right. So I put a star on number 18. We'll come back and grab that next time. But I wanted to go through, because we did talk about circles a little bit already. So I wanted to just kind of put the finishing touches on that. So we'll move on to the next page. A lot of it is a rehash of stuff I talked about earlier in the class, which is really nice because we don't have to worry about starting from the ground floor. We could just build off of what we already know. So, not going to bother with this. This is the general form of a conic section. Pretty hideous looking equation, but this gives us circles, hyperbolas, ellipses, and to some extent parabolas, but we're not really going to do too much with those, right? The definition of circle I gave here. Oh, and by the way, you don't have to memorize the word ellipse and hyperbola. I've lessons for that. So we'll talk about those next time, probably. Definitely. But I wanted to talk to you about how to go from the messy form to the standard form of a circle. All right, so that's on page 17. So what we do is group X terms together. And Y terms together. All right, then we complete the square for X and Y. Move the constant to the other side. Your answer should be in the form of X minus H squared plus Y minus K squared is equal to R squared. All right. So we group the X terms together and the Y terms together. Complete the square for X and Y, move the constant to the other side, and our answer should be that of a standard form of a circle, right? Together is the third word of the day. Is that we're going to solve an example together. Right, so the directions kind of vague. It doesn't really say put it in standard form, but it does say find a center in the radius. And it's like, okay, well, how do you do that unless you put it in standard form? You know, you could get a calculator involved, but sometimes you can't pull the relevant information easily from a calculator, right? As we've seen. So group the X and Y terms together. or x terms together and y terms together. So I'm going to write this as x squared plus 6x. I'm going to leave a little space to complete the square, plus y squared minus 4y. I'm going to leave a space to complete the square, minus 23 is equal to 0. All right, so I'm going to complete the square for the x's, and I'm going to do so for the y's. And the result should give me a perfect square trinomial, which is factorable. All right, so let's kind of simplify the process a little bit. To complete the square, use b squared divided by 4a. All right. There's other ways to do it, but this is the most streamlined approach. It's formulaic, admittedly, but it's also something where, you know, I don't have to write down 10 steps that are the algorithm for completing the square. It's just use this formula. All right. So in every quadratic, you have a coefficient in front of the x squared term, or the squared term, I should say, and a coefficient in front of the non-squared term. This is a, this is b. We'll worry about the y's in a second. So b squared over 4a is going to be equal to 6 squared over 4 times 1. Now, if you're proficient in completing the square, you do it any, you know, like the way that you know, that's fine, right? As long as it works. You'll know in a minute if it does. All right, so that gives me a 9, positive 9. So I'm going to put a plus 9 in here. All right, there's an understood 1 here. So that's another a. And this is a b. So do another b squared over 4a. So negative 4 squared over 4 times 1. 16 over 4 is 4. So positive 4 goes in here. Now, with all the markups and everything, it's kind of messy. But we'll get to that in a minute. All right. Also, something to keep in mind, you can't just add a number to one side of the equation because you feel like it. You have to add it to the other to keep it balanced. So plus 9 plus 4. So I'm looking at, on the left-hand side, x squared plus 6x plus 9 plus y squared minus 4y plus 4. And since we're going to have to move this term away anyway, why not just do it now? So I'm going to add the 23 also. All the constants should be on the other side. All right. So 9 plus 4 is 13, plus 23 is 36. So I'm going to factor this. That's going to be x plus 3 times x plus 3, so x plus 3 squared. Then this one, y minus 2, so y minus 2 squared. Bring down that plus sign that's in there. And we get 36 as a result. All right. Now this is the equation in standard form. So from this, we can say that the center, which is HK, is going to be -3, +2. All right. And that's because the minus is already built into the equation. So if H was substituted in, and let's say I only substituted a +3, it would become x minus 3. That's not what we have. And there has to be a double negative for it to become positive. All right, the K value is 2 because I can directly put in a 2 here and not have any trouble whatsoever. All right. The radius is whatever the square root of the constant term is. So R is equal to 6. Do one more, and then I'll star one for you. All right, but it's very procedural, which, you know, some people love, some people hate. Procedural means that there's a process that needs to be followed, right? But maybe you don't want to follow a process. You just want to state what the correct answer is and be done with it. Well, unfortunately, not the case for these kind of problems, right? So group the X's together, group the Y's together. I mean, a very first step could be to get rid of that constant term. So I'm going to rewrite x squared minus 8x, y squared plus 10y. And I'm just going to bring that 25 over, make it negative. Subtracting it from both sides. I'm not doing any magic. All right. We have the 1. That's my A. The negative 8 is my B. B squared over 4A. And by the way, that 4 is necessary. Even though I'm sorry, the A is necessary on the bottom. Even though the A values have been 1, they won't always be 1. All right, so got to keep that in mind. So negative 8 squared over 4 times 1. 64 over 4 is 16. So plus 16 on this side, plus 16 on that side. Same idea for the Y's. Understood 1. Got the B. B squared over 4A. 10 squared over 4 times 1 is 25. So plus 25 plus 25. All right, use highlighters here. Kind of make it a little easier. All right, so if I factor this, x minus 4, so x minus 4, the quantity squared. Factor this one, y plus 5, so y plus 5, quantity squared. Add them, set them equal to 16. So now I have my circle equation in standard form. My center, 4, negative 5. And my radius is equal to 4. And a little star for the last one. Probably the best star I've ever drawn in my life. All right. So at this point, I'm going to stop the recording.